Copyright in these lectures is either owned by the ANU or a third party who has licensed the ANU to use it. Students may use the recording for personal study only. No lecture may be communicated online, copied or shared without the prior permission of the ANU.
Okay, let's start today's lecture. And firstly, welcome back, and hope you have a very good semester break. And secondly, some announcement. So the most important announcement today is about the assignment. And I have already released the assignment, I think, right before yesterday. So the due date is 26 September, so that means next Wednesday. So you will have almost 10 days to finish this assignment 1. So any questions about this course in the first half of the semester, or any question about the assignment?
Yes. Do I go? Do you want me to go to the microphone?
You can, if you can. Thank you.
Yeah. So do we round all of our answers to four decimal places?
Sorry?
For the assignment?
For the assignment? So,
Do we round all of our answers to 4 decimal places?
sorry, I still cannot understand your question.
So...
I think it's said in assignments.
Okay, yeah.
Round to 4 decimal places.
Yeah, was
okay.
that for all
Okay,
of
4
them?
decimal places? Okay.
Yeah.
So about that question, so let's just have a look at it. So I think for some questions, I think you can see very clearly that you need to round to 4 decimal places, correct? For instance, in this question 1a. However, for some questions, and I remember there is one question. For instance, in this question, compute and show the sum of the squared error for the fitting model in this question and question 1a respectively. So when you show the sum of the squared error, you can consider to round the sum of the squared error to 4 decimal places. I think that's okay. But I think the more important question here is that which one is smaller. So in this case, I think you can consider to round the answers for all the questions into 4 decimal places. But for some questions, it doesn't matter. More questions about the assignment?
Sorry, I did have another question. Just checking, it is 4 decimal places, not significant figures.
So what's the meaning for 4 decimal places, not significant?
Oh, no, I mean, I know the difference, but just checking which one we're doing.
I still do not understand. So what's the meaning for the significant figures?
Oh, so say that I had a number like 0.002536. That would be to 4 significant figures.
Okay. I think just round to 4 decimal places, not significant
Okay.
figures.
Thank you very much.
Yeah, because yeah, because I think it's clear for decimal places, not significant figures. Okay? Yeah, sorry. Because usually in my assignment, I usually just request to round to 4 decimal places, not significant figures. So, sorry. Sorry about I misunderstand your question. More questions about the assignment? And if you look at the course outline, I think this PC. If you have a look at the course outline, you will find that due to the redeemable nature of the assignment, the late submission will not be accepted without appropriate documentation. So, if you do not submit your assignment before this date, so that means you cannot submit late for this assignment, actually for both assignments. So you do not need to submit it to me again, and also you do not need to send an email because the assignment is redeemable. So if you do not submit your assignment, the weight will roll over to the final exam. Okay, so that's about assignment. More questions? Okay, so let's continue our previous topic. So maybe after this 2-semester break, so maybe you have already forgotten some part of the this topic, which is called variable selection. So what's the meaning for the variable selection? So if you have a look at this output, so the meaning for the variable selection here is that we just want to, for instance, in this example, we have a lot of variables. We have 5 variables. Take us income, year, public, expenditure, rank in this example. However, we only want to select a subset of these variables. So that means we only want to get we only need to consider several variables in this example. So the result here is that we only select income, years, public, not public because it's 0, sorry. Expenditure and rank. So that means we only select several variables based on some criterion we make. So in order to explain the criterion, firstly we consider to use our F statistic to help us to determine 2 criteria. The first one is criterion A. So what's the meaning for criterion A? So that means in this, for instance, in this backward elimination step, if we have J variables, we need to determine whether or not we should eliminate one variable. So the criterion A is just to be used, is used to help us to determine whether or not we should continue. So that means whether or not we should eliminate. And also we have criterion B. So what's criterion B? Criterion B is that if we determine to continue, so that means if we determine to eliminate one variable in this step, so which one variable we should eliminate. So that's the meaning for this criterion B. And how can we make those criterion A and also criterion B? So that's directly from our idea of F-test. So because F-test is used to compare the model with more variables, usually we call it full model, and also the model with less variables, usually we call it the reduced model. So by using this standard, we can use the F statistic to make our criterion A and also criterion B, such that we can complete this backward elimination or forward selection step. So that's the idea behind this sequential variable selection techniques. So in the previous topic, I think in the previous lecture, so basically I just try my best to explain it by using this flow chart. So what's the meaning for criterion A and what's the meaning for criterion B by using these two examples. You can consider it as the numerical examples. So, but one thing I didn't mention here is that, so I think for criterion A, basically it is from the idea of the F-test. But for criterion B, so why it is reasonable, so I didn't mention about it. So why here for this, for instance, I just explain it for the backward elimination step. So why for backward elimination step, why this criterion B is reasonable? So firstly, in order to proceed to this criterion B, firstly we need to have the result of continue. So that means we actually determine to eliminate one variable. So if we have this, we already have this conclusion or the decision, so we need to consider which one variable we should eliminate. So what we can do here is just to compute all the F statistic. And if you just read this criterion B, so what's criterion B? Criterion B is the F statistic is the smallest. So why? We need to consider the F statistic is the smallest. So in order to explain this, you can have a look at the formula for the F statistic. So the F statistics equals to sum of the squared error reduced minus sum of the squared error full divided by D, and here D equals to 1, and then divided by sigma hat square full. So let's just move this formula here. So the F statistic equals to SSE reduced minus SSE full divided by D, but D equals to 1 here, and then divided by sigma hat square full. So here, what's the reduced model, what's the full model? So the reduced model is the model with less variables, and the full model is the model with more variables. So, based on this formula, we can see that for all the F statistic here, we have a lot of F statistic here. The full model is the same. So that means we only have one full model, the model with more variables. So the only difference for this F statistic is that they have different sum of the squared error, right? So here, for the criterion B, we find those variables which has the smallest F statistic, because the sum of the squared error full and also the sigma hat square full are all the same for all these F statistics. So that means we actually find those variables which have the smallest sum of the squared error, or you can call it sum of the squared error reduced, because we have less variables for the reduced model case. So these two are equivalent. So now you can see the logic here. We actually want to find those variables which can lead to the smallest sum of the squared error. So if you still remember the meaning for the sum of the squared error, sum of the squared error just measures the goodness of fit for the regression model. So you can see that the criterion B here is actually from this minimize the sum of the squared error for the regression model. So remember this because in today's topic, we are going to actually use sum of the squared error to help us to accomplish variable selection instead of the F statistic. So after review it a little bit and let us look at our example. So for our example here, we use this package which is called WLE to help us to accomplish the variable selection, a sequential variable selection by using F statistic. But unfortunately, reminded by one student, I think if you look at the discussion forum, this package is no longer available. So you can look at it here. So it says the WLE was removed from the CRAN. CRAN, basically, you can consider it as the official library in our official R website. So after 2018, so that means we can, if you want to, you can try to install this package manually, but basically, if you use the install.packages function, you cannot install this package automatically. So because of it, so I think I need to explain it. How can we deal with this problem in this course? So my suggestion here is that because this package WLE is no longer available, so in this course, you are not required to use this package. I think in tutorials, assignments, and also exams. So in exams, you will not have a chance to use R, but I think this part of the codes and also output will not appear in your exam too. But even if we cannot use this package directly, but the idea behind it, so that means the idea for variable selection by using this F statistic, because I think F test is the first thing you have learned to use the F statistics to accomplish variable selection, and also that's the direct way. So the idea behind this is still required. So that means, for instance, if I just give you this ANOVA result, so ANOVA result for a lot of F tests, and you still need to know how to use those ANOVA results to accomplish variable selection. For instance, I kind of give you this numerical example. So if I give you those F statistics from the ANOVA result, and you need to consider to use this flowchart to determine whether or not you should continue or which variables you should select in this step by using the ANOVA output. So that does not affect anything for the understanding of this sequential variable selection. But in order to realize it, because this package is no longer available, you cannot automatically get the variable selection output, like something here. So if you are really interested in this variable selection by using the F statistic, I think you have two choices. The first one here is that you can actually install this package manually, but it takes time. You can try to Google install this package manually, and then you can have a try of that. But I do not recommend that. So in this case, because it's not available anymore, so I will not require you to work on this. And the second Second option here for this variable selection among sequential variable selection by using the F statistic is just to consider to use this by using this ANOVA function to write the variable selection by yourselves. It's also a very challenging task. You can actually use this flowchart to accomplish the variable selection all by yourselves. So basically, you can consider that you can write a new package for this, but still it's challenging. So if you are interested in those two, I think I'm really happy to help you during my consultation hours. But for this course, I think the bottom line here is that you still need to understand the idea behind this variable selection by using this F statistic. So the reason why I think this package is no longer available, I think there are a lot of reasons, but I think the true reason here is that actually in practice, we do not use this sequential variable selection by using F statistic to accomplish variable selection a lot. I think the true reason here is that we actually consider other criterions to help us to accomplish the variable selection, and those criteria are more popular, so that's the reason. So in today's in today's lecture, we're going to talk about sequential variable selection by using other statistical measures. So I have already mentioned that we need to determine criterion A and also criterion B for us to proceed the forward steps and also backward steps. And for criterion A and also criterion B, earlier we only considered to use the F statistic to determine these two criterion. And also we explain the logic behind using the F statistic when we consider the criterion B in the backward elimination step, and it's kind of related to the sum of the squared error. So in this case, how about we do not consider to use this F statistic because the package for the F statistic is no longer available. You can consider in this way. But the true reason here is that actually using other kind of statistical measures is more popular, I think, in practice. So how can we do the variable selection without using the F statistic? So the idea here is that I think is you can consider because I have helped you review it. So the idea here is that for this multiple linear regression model, I think for most of the times we are seeking the goodness of fit. So that means we are seeking small sum of the squared error. So that's our first goal for the multiple linear regression. But another goal here, so that's for the variable selection here, is that we want to find a small number of variables to construct the multiple linear regression model because we do not like to involve a lot of irrelevant variables in multiple linear regression model. And you can see that clearly these two goals are contradicted. So if you remember, I think, if you remember the one very important conclusion in the previous topic about F-test, so usually more variables results in, not usually, I think it's always more variables results in the decrease in sum of the squared error. So these two goals are contradicted. So in order to balance these two goals, so what we can do here is just to consider some measures, statistical measures, which can compromise between the goodness of fit. So that means the sum of the squared error and also the number of the explanatory variables. So that's the idea behind this. We need to balance these two. So how can we do that? So we actually propose something which actually balances these two. So this one is adjusted R-square, if you still remember. So what's the adjusted R-square? The adjusted R-square is for this model with j variables. Here is that it equals to 1 minus sum of the squared error divided by n minus j plus 1, and then divided by sum of the total divided by n minus 1. So that's directly from the previous topic. I just copied the formula here, but I only consider this for j variables. So you can see here in this formula, sum of the squared error is in the formula, and also the number of the variables j is also in this formula. So in this case, this adjusted R square balances sum of the squared error and also the number of the variables. And in order to look at the intuition in this adjusted R square, so let's look at what's the meaning here for this. Usually we want to have a larger adjusted R square in the multiple linear regression model. So why we want to have this larger adjusted R square? So for instance, let's consider two candidate models. So what's the meaning for the two candidate model? So for instance, we consider like the model with three variables, x1, x2, and x3. And another case is the model with also another three variables, x2, x3, and also x4. So for these two models, their number of the explanatory variable j is the same. So in this case, these two models both have the three variables. So the number of the explanatory variables are the same. Then, from our intuition, the model with the smaller sum of the squared error, because the sum of the squared error measures the goodness of fit for the regression model, is preferred. Equivalently, if we have a smaller sum of the squared error, so that means we have a larger adjusted R square. So in this case, if the number of the explanatory variable j is the same, then we need to consider the model with the larger adjusted R square. So that's one case for this, how to use this adjusted R square. And another case here is that if we have the same sum of the squared error, so that means we have the same goodness of fit for the model. So what we need to do here is just to consider the model with smaller number of the explanatory variables. Because for variable selection, we actually need to, only want to use a smaller number of the explanatory variables to determine the regression model, and we always prefer the model with less variables. So if we have smaller number of the explanatory variables, so that means here in this formula we have the smaller number of the variables. So, and based on this formula, that also is equivalent to larger adjusted R square. So in both cases, we always have this situation that the larger adjusted R square is preferred. So in this case, we have this criterion by using this adjusted R square. So we always prefer the model with larger adjusted R square. And in this case, we balance the goodness of fit for the regression model and also the number of the variables. So that's the idea for the adjusted R square. And it's straightforward, and also you have already learned our adjusted R square, so you are more familiar with that. But instead of the adjusted R square, we actually have other kind of criterion, other criteria to help us to balance these two, to balance the sum of the squared error and also the number of the variables. So we have this archaic information criterion and also the Bayesian information criterion. And I think the archaic is the most famous Japanese statistician. So for these two criterion, so because the idea behind this criteria is just to balance the sum of the squared error and also the number of the variables, you can see we just have different ways to balance these two. So the only difference between the AIC and also the BIC here is the weight. So usually n log n is larger than 2, for large n. So that means BIC actually assigns a larger weight for the number of the variables. So that's the only difference. So that means in BIC, the number of the variables is more important because it assigns a larger weight. So that's the difference between AIC and BIC. But the idea behind AIC and BIC is similar to adjusted R-square. They are just used to balance the sum of the squared error and also the number of the variables. So similarly, we have these two cases. You can use these two cases to understand the meaning of AIC and BIC. So if we have the same number of the explanatory variables j, so we always prefer the smaller sum of the squared error. And based on this formula, it's equivalent to consider the smaller AIC or BIC. Similarly, if we have the same number of the if we have the same sum of the squared error, we always prefer the model with less variables. So equivalently, we prefer the model with smaller AIC and BIC. So if we use the AIC or BIC, we always prefer smaller AIC and BIC, or BIC. So compared to this adjusted R-square, so for adjusted R-square, we always prefer larger adjusted R-square. And for AIC and BIC, we prefer smaller AIC and BIC. So I think that's the idea behind this adjusted R-square, AIC and BIC. I think by using one sentence is just to balance the sum of the squared error and also the number of the variables. Any questions so far? So this idea is totally different from the F statistic, but you can see there is some connection, especially for this sum of the squared part, sum of the squared error part. Any questions? Okay.
Sorry, what does N stand for?
Okay, very good question. So what's N? So N is the, so because after two weeks, so you may have already forgotten something. So N is the number of observations. So that means you have the y1 to yn, and also x1, 1 to x1n, until xj1 to xjn. So that means you have the nth observations of y and x. More questions? Okay. Okay, I need to. Yeah, sorry, I always listen to the echo in this theater, so I cannot hear your question very clearly. Mm-hmm. Okay, so the student asked this question for the adjusted R-square, whether or not we should compute it manually, or we can just use some package, like we can use the LM function to compute the adjusted R-square. So for the adjusted R-square here, I think you can actually use the LM function to obtain this result directly. So that you can use the LM function. So if it's in your tutorial or in your assignment, I think that's more direct. But I think based on this formula, you can actually compute it based on sum of the squared error and also the sum of the squared total. So that means if you have these two measures, you can compute it manually. But I will not require you to compute the sum of the squared error. I think manually, I think for too many observations, like for instance, n equals to 100, basically that's not possible. So I think the bottom line here is that if you can find for instance, in your final exam, if you can find the measure like sum of the squared error, and also the measure sum of the squared total, for instance, in some R output, and then you need to use this formula adjusted R-square to compute the numerical value here. So because I think I explained a little bit about the sum of the squared error, so how to compute the sum of the squared error, and also the relationship here for the sum of the squared error between the sum of the squared error and also the sigma hat. So maybe I just try to find some output to help you. So actually in the output you can actually to obtain the adjusted R square. So this is the adjusted R square, right? And here we have the residual standard error. So what's the residual standard error? So basically it's the sigma hat. So what's sigma hat? Sigma hat just equals to sum of the sigma hat square, sum of the squared error divided by m minus k minus 1, if you still remember. So what's m minus k minus 1? M minus k minus 1 is the number of the degrees of freedom. So in this table, so here, that's the m minus k minus 1. So that means by using this residual standard error and also this number of the degrees of freedom, you can actually compute the sum of the squared error, right? And for the sum of the squared total, so what's the sum of the squared total? For the sum of the squared total, it equals to yi minus y bar, if I still remember, square and I from 1 to n, the summation of I from 1 to n. So straightforwardly, we cannot, if n is very large, straightforwardly, you cannot compute it manually. But for sum of the squared error, if you have this output here, as I have already explained here, you can actually compute the sum of the squared error. But by using this output, we also have another measure which is called R square. So R square equals to sum of the squared of regression divided by sum of the squared total. So that equals to 1 minus sum of the squared error divided by sum of squared total, right? So because by using this residual standard error here, we can compute the sum of the squared error. So that means this sum of the squared error can be computed manually by using this R output. And also the R square here is provided. So that means R square is provided. So that means we have this equation of sum of squared total. So by solving this equation, we can compute the sum of the squared total, right? But I think that's, I think I answer more of it. But what I want to say here is that you can actually use some part of the results in this table to compute the sum of the squared error and also the sum of the squared total. And also, because you can compute sum of squared error, sum of squared total, you can compute sum of the squared of regression. So that equals to sum of squared total minus sum of the squared error. Because we always have this equation, sum of squared total equals to sum of the squared error plus sum of the squared of regression. So I think I answer more of it. But by using this output, we can obtain this adjusted R square directly. So I think that's my final answer of this question. More questions?
Sorry, would you mind going back to the slide that had the R output?
Yeah.
Thank you. Yeah, did you say that the residual standard error equals sigma hat squared or sigma hat?
No, sigma hat.
Yeah, thank you.
Yeah. So I think the reason why I write in this way is just to, because it's easier to write, but I think you are correct. So here, this is the sigma hat. So what you need to do here is just to consider the square root of the sum of the squared error divided by the number of the degree of freedom. Yeah, thanks for your reminder. Yeah, sure.
So for the model selection, when do we use adjusted R-squared and where do we use AIC or BIC?
Okay, so another very good question. So we actually have different measures to balance this sum of the squared error and also the number of the variables. So you can see the way to balance these two are different for these three measures, right? So that means by using these three measures, we may have different variable selection results. So when we have different variable selection results, I think a natural question here is that which result we should consider. So in order to answer this question, you need to wait a little bit, and I hope that in today's lecture, I will explain to use the cross-validation to determine which one with adjusted R-square, AIC or BIC should we use in real practice. So that means I think it's common in statistics that we propose a lot of different methods to achieve the same purpose, but sometimes I think in practice, in real questions, some measure may be better than the other measures. I think for most of the questions, I think you will find if we consider these three measures, adjusted R-square, AIC, and BIC. So in practice, we find that usually AIC is really good for prediction, but that's from the experience. Sometimes it's not correct in some specific question. And BIC can select the variables very accurately. So that's what I can see in real practice. But indeed, in this course, we need to determine which one we should use, but we are going to talk about a method which is called cross-validation to solve this problem. More questions? So let's proceed, and you can ask more questions, because you will find that I'm going to repeat something in the previous lecture. So here, in conclusion, these three measures all balance this goodness of fit. So that's sum of the squared error and also the number of the variables. And the difference between AIC and BIC here is that for BIC, the number of the variables is more important because it assigns a larger weight. Because in BIC, the number of the variables is more important, so usually BIC selects the model with less variables. So that is from this formula, because log n, this weight is larger than 2, so that means it assigns a larger weight to the number of the variables. So the number of the variables contribute more, I think, in BIC. But we always prefer smaller BIC, so that means we always prefer the smaller number of the variables. So in that case, BIC always select less variables compared to AIC. And I think maybe in the later examples, you will see that BIC usually selects less variables. So in order to use these three measures to help us to accomplish the sequential variable selection, I'm going to talk about the flowchart again. So in order to talk about this flowchart, I actually need to unify these three measures. So in order to unify it, I just use this measure equals to minus times adjusted R-square, or measure equals to AIC, or measure equals to BIC. And here, the standard here is that we always prefer smaller measure, and because we prefer smaller AIC, BIC, or we prefer larger adjusted R-square. So I just use this -1 to unify these three. So let's look at this flowchart for the forward selection step. So similarly to the variable selection, by using the F statistic, for this forward selection step, we need to determine two things. The first thing is that whether or not we should continue. So that means whether or not we should add one variable. We need to determine whether or not we should add one variable, so we need to use this criterion A. And also we need to determine whether or not if we determine to add one variable, so we need to decide which variable we should add. So that's criterion B. But here we do not use F-statistic anymore. We consider to use those three measures. So those three measures are AIC, BIC, and also -1 times the adjusted R-square. So how can we do that? So still here, let me just give you some numerical example to help you to understand why we can determine the criterion in this way. So this is the flowchart for the F-statistic. We use these two examples. The first example is stop, and the second example is continue. So similarly here, I'm going to use these two numerical examples to help you understand this flowchart. So the example 1 is stop. So I'm going to use the blue pen. So the example 1. So the example 1 is stop. So what's the meaning stop? Stop just means that we actually stop here. We do not add one variable. So in which kind of case we need to stop? For instance, here in this example, I just used blue pen to represent this numerical example. This measure 0, so measure 0 means the AIC, BIC, or adjusted R-square for this model with J variables. So that's the meaning for measure 0. For instance, here, we actually have this measure 0 equals to -2. So by using these variables and also by using the data, we can compute the AIC, BIC, or adjusted R-square, or -1 times the adjusted R-square. So maybe it's, I think in this case, it's not -1 times adjusted R-square. I think usually, even if for adjusted R-square, it's really close to, usually it's less than 1. It's between 0 and 1. So in this case, I think you can consider that it's the value of AIC. The AIC equals to -2. And also we can compute all the measures here for this case, for those cases when we add one variable. So in this case, we can have this measure, for instance, here. This first one equals to -1.1. This equals to -1.2. And this equals to 1.3, and this equals to 1.4 minus. So in this case, if we compare all these measures, we can find that the smallest one here is -2. So that's the measure 0. So that corresponds to x1 to xj. And remember our standard. So our standard is that we always prefer smaller measure. So that means this model, x1 to xj, with variables x1 to xj, is actually preferred in this case. Because this model is preferred, so that means we do not need to proceed to consider adding variables. We actually do not need to do that because this model is preferred. So in this case, we stop. We do not consider to add any variables. So that's the example, numerical example, that we stop because we have the smallest measure. We have the, for instance, we have the smallest AIC in this case with x1 to xj variables. Also, we can consider another numerical example, example 2. So let's continue. And for example, this example, I use a red pen. So in this case, let us just consider this measure equals to -1. And for the other measures, they are the same. So now what's the difference here? The difference here is that for this measure -1 is no longer the smallest. We actually have smaller measures for those cases when we add variables. We had -1.1, 1.2, 1.3, and 1.4. They are all smaller than -1. So in this case, we should consider to proceed. So that means we consider to continue and try to add one variable in the model. But a natural question here is just to answer which variable we should add. So that's exactly criterion B. So the criterion B means that still remember the standard. The standard is that we always prefer smaller measure. So in this case, the smallest one here is -1.4. So the variable selection result here is that we actually consider to select the variables x1 to xj, and also we consider to add this variable xk, because the corresponding measure, or you can consider the corresponding AIC or BIC, is actually the smallest one among all these kind of situations by adding one variable. So that's criterion B. So that's the forward selection step for J variables by using this those new measures, AIC, BIC, and also adjusted R-square. And also, in order to complete the steps, we actually need to start from the model with 0 variables. And in the previous lectures, a lot of students asked me this question, so what's the meaning for the model with 0 variables? So that just means the model with intercept only. And usually in LM function, you can consider it as y tilde 1. So that's from our code. So we start from this model with 0 explanatory variables, and then we just try this procedure. And what we can do here is just to let j equals to 0 in the previous page. And then we just try the criterion A and also criterion B to determine whether or not to actually use criterion A to determine continue or stop. And if we consider to continue, we use criterion B to determine which variable we should add. And then we're going to add one variable. And if we determine to add one variable, and then we can proceed to consider the forward selection for this one variable. And similarly, for one variable, what we need to do here is just to let j equals to 1 in the previous page. And we can keep on doing that until the first time we achieve the result of stop. So that's, for this complete step, it's exactly the same compared to the forward selection by using the F statistic. So the only difference here is the criterion A and also criterion B, because we propose new measures to do that. So let's just take a 10 minutes break, and then we are going to talk more about how to use this measure to accomplish the sequential variable selection. Okay, let's continue the second part of today's lecture. And first of all, any questions so far? Okay, so let's continue this variable selection, still variable selection, really a long topic, and hope that we can finish it within this week. And we are going to focus on the next half of the semester topics about the discrete response variable. But for now, let's just try to finish this variable selection in this week. So we use these two numerical examples to help you understand the detailed variable selection step for this forward selection of J explanatory variables. So symmetrically, let's just look at the backward elimination step. You will find a lot of similarity between these two. So for the backward elimination step, you can consider it as the opposite procedure for the forward selection step. So what we need to do here is that we have J variables, and we want to determine two questions. The first one is that whether or not we should eliminate one variable among these J variables. And the second question is that if we determine to eliminate, which variable we should eliminate. So in order to answer these two questions, I just use this flowchart to help you understand. And similarly, I just use two examples. The example one is stop. The example one is always stop. So I just do the exact same, just write down the exact same figures if you look at those values of measures. So here, let's consider the measure 0 equals to 2. So what's measure 0? Measure 0 is the AIC, BIC, or -1 times the adjusted R square. And if we have the data and also if we have those variables, we can compute those values. And here, the value measure 0 equals to -2, 2. And also we can consider to eliminate eliminate one variable among those variables. So we have these J situations. So for each kind of situation, we can compute the measures. Here, for instance, this measure 1 equals to -1.1, 1.2, 1.3, and also 1.4, or minus. So in this case, similarly, this -2 is the smallest. So the standard for this AIC, BIC, and also minus adjusted R square is consistently that we always prefer the smaller measure. So because this -2 is the smallest, so that means the corresponding variables or the corresponding model is more preferred. Because this model with x1 to xj is more preferred, I cannot use, is preferred. So in this case, we do not need to proceed to eliminate variable. What we need to do here is just to stop here, because based on the standard of AIC, BIC, and minus adjusted R square, this model with J variables is the best, because its corresponding measure is the smallest. So that's the situation that we stop. And also we have the situation continue. So for the continue case, we just consider this numerical example. For instance, this measure 0 equals to -1. And for all the other measures, I just give those the same values. So in this case, because we actually have those measures, these measures are smaller than -1. So that means by eliminating one variable, we actually obtain a smaller measure. So remember, the standard here is that we always prefer the smaller measure. So that means those models with less variables are preferred. Because the models with less variables are preferred, so we consider to continue. So that means eliminating variable can lead to a smaller AIC, BIC, or -1 times adjusted R square. So we consider to proceed. So if we consider to proceed, we need to find the model with the smallest measure. And here, -1.4 is the smallest. So that means our variable selection result here is x1 to xj minus 1. So that's our variable selection result. Always find the model with the smallest measure. So that's the idea. So that's for the backward elimination step. Any questions? And for the complete step, I think something very similar. We start from the model with all the variables, and firstly we try our criterion A to determine continue or stop. So if we determine to continue, we are going to use our criterion B to determine which one variable we should eliminate. And after we eliminate that one variable, we are going to have k-1 variable. So we keep doing on that by using criterion A and also criterion B. And finally, we get this result of stop, and then we just stop and get our variable selection result. So I think that's similar in the previous case. And also we can consider this stepwise. So for the stepwise, we just consider this combination of forward and also backward elimination step. So I think that's all I need to mention, because this basically I just copied this page exactly from the page for the stepwise selection by using F statistic. And these three methods usually lead to different variable selection results, and later I'm going to use the cross-validation method to solve all this kind of inconsistent result problem. So before I talk about cross-validation, let's look at this variable selection by using the AIC, BIC. So how can we accomplish that by using the R package? And what you need to do here is just to use this package MASS, and I'm sure that this package is still available because this package is really important and is really popular. From my perspective, it's more important and more popular than the package WLE. So maybe that's the reason why the WLE is removed from the R package library. And so let's just look at this, how to use this package. And firstly, let me just introduce some R code maybe I didn't mention before. So this LM function, so we have a new use for this LM function. We can use this data argument. We can consider data equals to x, and x is the data frame consisting of all the explanatory variables. And when we specify like this, we can just use this point here to represent that we actually consider to fit a model with all variables in X, and X is a, if you still remember, so X is a data frame with all variables. So that means by using this dot, y tilde dot, so that just means that we fit a model with all the variables. And after we install this package, and also we can use library to load this package, we can use this step AIC function to accomplish the backward, forward, and also stepwise variable selection techniques. So for this backward, what we need to do here is just to input this fit. So what's fit? Fit is the output of this LM function by considering all the variables. And also we need to, I think we need to specify the variables here. So data equals to x. So x is just the data frame with all the variables. And you can have a try of that by using this step AIC function, and it will return a lot of result. So because I have this page limit, so I will not try that. But I think I will assign tutorial questions for you to try this step function, and this step AIC function actually returns a lot of output. But in order to look at the final variable selection result, what you need to do here is just to use this summary output function. And this summary A just returns the final variable selection result. So you can see that at the result for this variable selection, we only have 4 variables instead of the order variables in this case. So these are the variable selection results. But in your tutorials, please do look at the output of this step AIC, because those output is really long. So you need to have a look at that. So that's how we use this step AIC to accomplish the backward. So this is actually the backward elimination step by using the AIC. And the final result here is that we actually select the variables, income, years, expenditure, and rank, these 4 variables. Any questions about how to use this package and this function? I think it's straightforward, right?
Oh, sorry. How do you know that we're selecting those 4? Is it just, it gives us a list of all the ones that we want to select?
So because of the echo, so I may need to, yeah.
Oh, yeah. Just checking. So the reason we know that we're including all 4 is just that it has the list of them?
The list of them?
That you've highlighted in red.
Yes. So this, those variables are the final variable selection result.
Okay, yeah, thank you.
Yeah.
That helps.
Yeah, the final variable selection result. So what's the meaning for these 4 variables? So that just means, so in your tutorial questions, if you have a look at the output of the step AIC, it actually gives you a path to get this final result of these 4 variables. But these 4 variables just means that if you try to consider this complete backward elimination procedure, so that means you will stop at these 4 variables, and then you get this conclusion that we select these 4 variables. So these 4 variables is income, years, expenditure, and rank. So that's the meaning for this output. By using this summary output function, it gives you the final result of this backward elimination step automatically. So if you are interested, you can have a look at the path to get this final result of these 4 variables, but in your tutorials. More questions? So it's really straightforward to get the final result directly. Okay, so let's look at another example, so maybe you can understand it more clearly. So in this example, let us consider the BIC. So the difference between AIC and BIC here is the weight. So in order to get the BIC result, we need to assign the weight. So here, how to do that? Firstly, we need to have n. So the student just asked me the question about n. N is the number of the observations. So in this case, it's just the length of y. So we have y1 to yn. And in order to accomplish BIC, what you need to do here is just to assign weight here. You need to specify the argument k. K equals to the weight. So for BIC, the weight equals to log n. So that's the only difference if you compare these 2 pages. This is for AIC, and this is for BIC. So for BIC, you can also use this step AIC function. We do not have the step BIC function. We only have this step AIC function by specifying a different weight. So that just means BIC. And we can also use this summary output to get these are the final result of the backward elimination by using BIC. So you compare these two, you can find that in this very specific real data case, we have exactly the same AIC and BIC result. And I think that's not common in real practice, and you will find that, I think, in your tutorials. Usually, BIC selects less variables. So that's BIC. Any questions? The only difference is the weight. So let's look at the stepwise. So for the stepwise, everything keeps similar. So the only difference here is the direction equals to both. Both just means stepwise, the forward and also the backward. So if you have a look at the backward here, the direction here is specified by the backward. But for the stepwise, you just need to specify it by using both. And also it gives the exact same variable selection output. So it's really an ideal case. So let's look at the last one. The last one is a little bit more complicated when we write the code. So for this one, I think you need to be very careful because it's totally different from the stepwise and also backward. So for this one, for forward one, firstly, you actually need to specify the model with no variables. So you use y_1. So that's the model. You need to get the model with no variables first. So remember, if you still remember the forward step, so the forward step starts with the model with 0 explanatory variables. So in this case, for the forward selection by using R, you also need to get the result by using this LM function to get the result of the model with no variables. Otherwise, you cannot get the final result. And also, you need to specify something which is called scope. So you still need to put this fit in this function. So that's your starting model. And also, you have the direction forward. So that means forward. But the most important thing here is just to specify scope. So what's the scope? Scope just means that you need to specify the range of those models you are interested. So in our case, the lower equals to tilde1 just means the model with no variables. And the upper equals to tilde takers, income, years, public expenditure, and rank. So that's the model with all variables. So in order to realize the forward selection, you actually need to specify the starting model and also the model with all variables. So that means you can consider it as the largest model. So that's the difference between forward and also backward. So if you have a look, so it's easier to realize backward by using R code, but it's a little bit hard here to realize the forward because you need to specify the scope. But in order to get the result, it's still similar. You can just use summary output and then you will get the result. So this is the final result of your variable selection. Any questions for this, how to use this step AIC function? So be careful about this forward case. So that's my suggestion. Any questions? Okay, so basically we have finished the one variable selection method, which is called sequential variable selection. So in conclusion, so what's the typical path for sequential variable selection? So we can use different measures, but I think the path is very similar. So the path here is that if we have this kind of forward, if we have the forward, we usually have this path as no variables. And maybe the next step, we just add one variable x1, and then the next step is x1 and x3, and so on and so forth, something like that, right? Because in each step, we only add one variable. Or we can have the backward. So what's the backward? So we start from all the variables. For instance, we start from x1 to x100, and then we consider to eliminate one variable. So here, for instance, we consider x1 to x99, and we can keep on doing that. So that's the typical path for the forward and the backward. So in each step, we consider to add or to eliminate one variable. But we also have a totally different method, which is called variable selection among all subsets. So it's totally different from the sequential variable selection techniques. So how can we define, or how can we consider this kind of method? We do not consider to add one variable each time or eliminate one variable each time. We actually list all possible kind of choices of the subset of variables. So what's the meaning for that? For instance, let's consider this simple case with two variables in total. So that means at hand, we only have two variables. The next step is just to list all possible situations of the combination of the variables. So we can have this kind of 4 situations. So that means we have the situation, we can consider this model with no variable. So we use this empty set, means no variable. And also we can only consider variable x1, or we can consider x2, or we can consider x1 and x2, both. So in this case, we just use those subsets. We can consider this as the subset. We can use this subset to represent one model. So here we actually have 4 candidate models. So the idea for this among all subsets here is that we try these 4 models, and then we find a statistical measure. For instance, we can consider this adjusted R-square, AIC, and BIC, and then we will have these 4 values, for instance, 4 values of AIC. We will have the AIC 1, AIC 2, and AIC 3, and also AIC 4. We will have these 4 values. And the idea here is that after we list all kinds of combinations, and we obtain all the values for this specific measure. And what we need to do here is just to find the model or the subset with the smallest measure. So that's the difference between this among all subsets idea and also the sequential. So for the sequential, we only consider to add or eliminate one variable each time. But for this among all subsets, we just list everything. So that's the difference. So I think I briefly explained the difference. So let me just explain it. You can read those details, but I think let me just still use this example. So for the variable selection among all subsets, we list all kinds of subsets here. So consider that we only have 2 variables, x1 and x2. So we can list all kinds of combinations of these variables. And for each combination, we can have this subset, and each subset can represent one candidate model. And after we list all of this, we can compute the AIC for AIC, BIC, or adjusted R-square. So I think you can just consider one of these 3. and still use some numerical value. For instance, this -1, -2, -3, and -4. And after we compute those values, we find that this -4 is the smallest. So that means this model with these two variables is preferred. So in this case, we get our variable selection result. So the result is x1 and x2. So that's the idea for this variable selection among all subsets. I think compared to the sequential variable selection techniques, it's kind of more straightforward by listing all kinds of situations. But for the sequential variable selection, for instance, for this kind of forward, so we start from the model with no variables, and then we try to add one variable. For instance, we try to add one variable x1, or we try x2, and we find that adding x1 is better by using the criterion A and also criterion B, and we continue this step and we try to add another variable x1 and x2. And then we are going to use criterion A and also criterion B. We always need to use criterion A and also criterion B to determine the final result. So that's the typical path for the forward. So compared to the variable selection among subsets, it's totally different. So one thing I need to say here is that usually the reason why I talk about the sequential techniques, I think in the beginning here, but not among all subsets idea, is that for the sequential idea is really computationally easier. But for this variable selection among all subsets is usually very computationally consuming. The reason here is that we actually need to list all kinds of choices for the variables. So if you consider this case, if we have 100 variables, x1 to x100, so how many subsets we are going to have for this 100 variables, or how many kinds of combinations we can have for these 100 variables? The answer is 2 to the power of 100. So that's too large. So you cannot list all kinds of situations for these 100 variables. But in this case, you can still use this sequential technique, because for this sequential technique, we always consider to add or eliminate one variable in each step, so that can save some computation. So that's the difference between these two. And for the variable selection among all subsets, we also propose a new measure. But this new measure, even though it's a new measure, but the idea is old. So the idea is still to compromise or balance two things. So to balance some of the squared error and also the number of the variables. It's just a totally different new formula, so it's a new measure. So how to compute this CP statistic? So firstly, we have the model with all the variables, so x1 to xk. So that means we always have this model with all the variables. And we can compute the sigma hat square, and we call it sigma hat square all. And if we want to define this CP statistic, we need to consider some candidate model. So that just means we have this model with only j variables, only a subset of the variables x1 to xk. And the CP statistics can be defined in this way, but it's hard to look. So I just write down in this way. So that means we balance the sum of the squared error and also the number of the variables. But it's a totally different way to balance it compared to AIC and BIC. So you can consider it as a new measure. But the idea behind this measure is similar, because based on this formula, you can see that if we have the same number of the explanatory variable, we always prefer the smaller sum of the squared error. So that means we prefer the smaller CP statistic. And if we have the same sum of the squared error, we always prefer the smaller number of the variables. So that is equivalent to consider the smaller CP statistic. So even if we have a different formula, a new measure, but the idea is similar. So because we have the similar idea, we still prefer smaller CP. So now we have a lot of measures. We have CP, we have AIC, we have BIC, and also we have adjusted R-square. So for the previous three, so usually we prefer the smaller CP, AIC, and BIC, but for the last one, adjusted R-square, we prefer the larger adjusted R-square. So by using this measure, what we can do here is just to consider all kinds of combinations of variables, so in this case, and then we can compute the CP1, CP2, and also CP3, and the CP4, and then we just need to find the smallest CP. So that's the idea by using this CP statistic. I think it's not different from the AIC and BIC, so the only difference is this new definition of this measure. Any questions about this CP statistic? So we have a lot of measures. We have CP, AIC, BIC, adjusted R-square, and also we have all kinds of different variable selection techniques. We have sequential variable selection technique, including forward, backward, stepwise, and also the selection among all subsets. So that means we actually have a lot of ways, we propose a lot of reasonable ways to accomplish variable selection. But the question here is that I think I have this question in this lecture, and also I have this question in the previous lecture. If we have the different results, variable selection results, so in practice, which result we should use? So that's really a natural question, because we have too many methods, but really in real practice, we may only need one method. So in this case, what we need to do here is just to consider this idea of cross-validation. So what's the meaning for this cross-validation? So that just means that, firstly, we are going to have a data set. For instance, we have the data set with observations 1 to 100. And then what we can do here is just to split this data set into two parts. The first part is the training data set. For instance, we consider from 1 to 90 observations as our training data set. And we are going to use this training data set for model fitting and variable selection. So that means you can try all different variable selection techniques and all different measures to accomplish variable selection. And usually those methods will lead to different variable selection results. For instance, you can use the AIC. For instance, you can use forward AIC, and you will get model 1. Or you can use the CP statistic among all subsets, and you will get model 2. So these two models are usually different. So the natural question here is that which model we should use. So firstly, use the training data set to obtain these two models. And secondly, you need to hold out some sample. For instance, in this case, we can hold out 91 to 100 for checking the variable selection results. So here, we have model 1 and model 2. And what you can do here is just to look at the prediction result for this model 1 and model 2 by using this test data set. So to look at prediction for model 1 and model 2, and find the model with the best prediction. And that model is your final result of variable selection. So that's how we use this cross-validation to actually to determine which variable selection method we should use in some specific real data example. But here, one thing I didn't mention is this: what's the meaning for this best prediction for this test data set? So we actually need some statistical measure to measure this best, to measure this, what kind of prediction is the best. So in order to do that, we introduce this mean squared prediction error. And this concept is very similar to mean square error, but you can see some difference. So here, in order to obtain this mean square prediction error, so firstly, literally from the name, what's the meaning for this mean square prediction error? Firstly, we have this mean, so that means we have this average. And the squared prediction error, so that means we have this, this is the squared. And also we have the prediction error. So this is our YL is actually the true observation. And YL hat is actually our prediction. But please be careful that this YL is actually our observation from the test data set. So what's the test data set? In this specific case, those are just 91 to 100 in this case. So in this example, this YL is actually, you can consider it as Y91 to Y100 in the example. So I need to specify it that we have this kind of example. So we only consider those response variables values in the test data set. We no longer consider those values from the training data set, because the training data set is only used to obtain the model fitting and also variable selection results. It's not going to be used as the, I think you can consider it as the variable selection checking or the prediction. And also we have the prediction. So here, this is the prediction. So what's this prediction? So if you still remember this prediction, it equals to, we consider it as the Y new equals to beta 0 hat plus beta 1 hat x1 new plus so on and so forth, beta j hat xj new. So we consider the variable selection result is x1 to xj from training data. And also those least square estimates, those beta 0 hat, beta 1 hat, and also beta j hat, they are also the fitting result from training data. But those x new are from the test data set. So that means we use the training data set to get the variable selection and also to get the model fitting, and then we use those model fitting and also the variable selection result to predict the response variable in the test data set. And then we compare the difference between the true value and also the prediction and obtain this mean squared prediction error. So you need to be very careful about this YL and YL hat here. it's different from what we have learned for the mean square error case. Any questions? And also the last one is n-test. N-test is number of the observations for the test data set. So in this specific example, n-test equals to 10. It's not equals to 100. And the best model is the model with the smallest error. So basically the smallest mean square prediction error. So that's how we use this training data set to get the best, how can we obtain the model with the best prediction. So the best prediction means the smallest mean square prediction error. So in order to explain it, let's look at some real data examples. So for this, I think this example is still the same. We just still use the SAT scores, just use the other variables to predict the SAT scores. So here, in order to accomplish the variable selection among all subsets, we need to use this package and hope this package is still available. And I think it's still available. So this is the used for the variable selection among all subsets. And then we just need to deal with the data by using our similar standard, I think. So for this part, I think it's similar to the previous case. And we can see that in total, we have 1 to 49 observations. Because we have 50 states in US, but we eliminate the Alaska state. So now we only have 49 states. And we consider the first 40 observations as our training data set. And we consider the last 9 observations as our test data set. So we firstly split the data into 2 parts, the training and also the test. And then we only use the training data set to obtain our variable selection result. So we just input this training and also training X and also training Y, and we specify the method CP. And for this M-best, I think I'm going to explain it in my next lecture. But by doing that, you can get this plot of the CP. So this is the so the y-axis here is the CP statistics, and also the for the x-axis we have the size. So what's size? Size just equals to number of the variables j plus 1. So that means 2 just means we consider the 1 variable. 3 just means we consider 2 variables. And 4 just means 3, 4, 5, 6. So for size is just another name of j plus 1. So by looking at this plot, we can find that if we only consider 4 variables, we are going to have the smallest CP because it's the smallest. And in this case, let us consider this, and I will explain more details in my next lecture, so do not need to worry about that. I just want to tell you here we can find the smallest CP and then we obtain our variables. So our variables can be represented by using 1, 0, 1, 0, 1, 1. So we only need to look at those ones, and that means we have x1, x2, x3, x4, x5, x6. So that means we are going to have x1, x3, x5, and x6. So this is our variable selection result. And also we can use the adjusted R-square method, and we still have the same result here. So that here we just use our training data set to obtain the variable selection and also the model fitting. And the next step is just to use the test the data set to obtain the mean square prediction error. So this is the mean square prediction error. So x1, x3, x5, and x6, and we can obtain the mean square prediction error here. So I think that's all I can say at the end of today's lecture. But do not worry too much about this real example. I just give you a very brief idea about what I am doing in this example, and then I will explain a lot of details in this example about how to use this LEAPS package to achieve the variable selection among all subsets, and how to compute the mean square prediction error for this cross-validation steps. So that's the end of today's lecture, and thank you so much, and let us meet on Thursday.